Welcome to today's presentation where we would like to show our approach for the design of load-specific component variants in sheet metal forming using fiber-reinforced hybrid beads. We'd like to start with a summary of the state of the art, and beads are channel-shaped load support structures which can be integrated in sheet metal components, as these three examples from the automotive industry show. To utilize the full stiffening potential of the beads, they must be aligned within the component. And in order to solve the resulting topology optimization problem, several numerical algorithms have already been developed. For example, the algorithm shown here by Macic aligns the beads according to the principal bending stresses within the part. To summarize, several targets can be met by integrating beads into sheet metal components. First and foremost, it's an increase in bending stiffness, or when lightweight design goals have to be met, an increase in the mass-specific bending stiffness. Second, a shift of natural frequencies can be used to deal with eigenfrequency and resonance problems. Third, the control of the deformation behavior in crash elements, which is important in the field of automotive industry. And number 4, flow guidance and surface enlargement of the beads show that they can be used for heat transfer problems. Based on these results, we propose an approach which can be used to derive load-specific component variants. Various designers face the problems that multiple component variants are subjected to various load cases. In order to meet lightweight design goals, it is useful to create several component variants. And since changes to the forming tools are quite costly in metal forming, we suggest instead of bringing in multiple reinforcement structures which consist of unidirectional carbon fiber reinforced plastics. So the goal of our approach is to combine the structural lightweight design of the beads with a multi-material lightweight design. Our approach therefore consists of several steps. In the first step, we manufacture and generate the basic sheet metal bead geometry using design and simulation tools. In the second step, we manufacture the hybrid bead, and the step can be subdivided in a surface structuring step and the lamination step. The last step of our approach is to measure the supportable loads of our hybrid beads, and for this validation task we performed several 3-point bending tests. To start with the first step of our approach, I'd like to show the resulting numerical analysis and the finite elements model which was created in Autoform. In the central area one can see the bead, and I would like to highlight this orange colored cross section, since in the next slide we will see an animation of the tool movement which is needed to generate the bead component. Here one can see the movement of the punch and the resulting bead geometry, which is also shown in the picture below. Actually, the design of the bead cross-section is more of an iterative process, since several optimization goals have to be met. First, it's an increase in the manufacturable bead height without the occurrence of tearing, since a larger bead height is associated with a larger stiffening effect of the bead. The second optimization goal was to increase the upper surface area of the hybrid bead, since this is the area where the fiber reinforcement will be placed, and a larger bonding surface, a larger adhesion surface will generate both a higher bond strength and a higher reinforcement effect due to the larger amount of possible UD-CFRP. So, based on the results of the numerical analysis, the toolset was manufactured and we were able to generate the basic bead geometry without the appearance of tearing for the DX56 steel. After the basic bead geometry has been generated, we can now make preparations for the lamination process. Since mechanical adhesion theory predicts a better bond strength with the UD fibers after the lamination, our goal was to use several pre-treatment strategies which increase the surface roughness in the upper area. As optimization goal, we choose the mean arithmetic height of the roughness in the upper bead area, and as reference we took the untreated sheet geometry, which shows only a very small amount of surface roughness. In the first step, we tried several chemical etching processes using both nitric acid and hydrochloric acid, but none of the etching times of 90 seconds and 300 seconds resulted in a significant increase of the surface roughness. So therefore, we examined two other kinds of surface structuring pre-treatments. The first is the laser processing using both a triple bidirectional pattern and a circular beam oscillation pattern. As one can see from these figures, the largest amount of surface structuring and of roughness increased was achieved with the triple bidirectional laser processing strategy. The last pre-treatment strategy mechanism we examined was sandblasting, and we used both injector blasting and pressure blasting, and even so the effect is not as strong as of the laser processing. We will see in the subsequent slides that we were able to generate a sufficient bond strength, so we identified two different kind of processes for industrial use of the pre-treatment strategies. When we analyze the resulting surface structure, we see certain differences between the laser structuring and the sandblasting structuring. Let's start with the sandblasting structuring. On a microscopic level, we can see both for the injector blasting and the pressure blasting at two different magnifications that we can achieve more of an irregular, sharp-edged surface structure. And the difference between the injector blasting and the pressure blasting is that the pressure blasting uses a higher amount of pressure, so the result is a more structured surface and a larger surface roughness increase. In comparison, here we show two macroscopic images of the resulting circular beam oscillation and triple bidirectional strategy, and one can see at first glance that it's more of a regular structure. Here the beams and the circular beams of the laser structuring process using circular beam oscillation, here more of a triangular-like structure for the triple bidirectional structure. And here the circular beam oscillation shows more of an anisotropic roughness enhancement in direction of the bead axis. On a microscopic level, we can see that there's more of a rounded structure, and here, for example, a molten and resolidified droplet can be seen. Similarly, here the trajectory of the laser generating these triangular-like structures for the triple bidirectional process, and showing also the more this rounded structure compared to the sandblasting process. Now we can manufacture the hybrid bead, and now there's the lamination process. And here I'd like to highlight this cross-section marked in light blue, and we took microscopic images of the manufactured samples. On the left side, one can see a so-called manual laminated sample in which the fibers are placed on the top surface area of the sheet, and afterwards the resin is brought in a hand lamination process. And second one, AFP-based sample, that means automized fiber placement sample can be seen, and using this technology, pre-impregnated fibers are laid upon the bead cross section. The second aspect I want to highlight in this slide is that there's a different height in the reinforcement structure, and this is a necessary condition for the manufacturing of load-dependent bead structures. When we analyze the microstructure of the resulting composite, we can see for the manual laminated sample on the left both the carbon fibers but also the connector thread, which is used to hold in place the UD fibers before the lamination process. And next to these connector thread fibers, one can see some associated porosity. Compared to the automated fiber placement strategy here shown on the right, where a much more homogeneous structure can be derived, and therefore this automated fiber placement strategy or this pre-preg based strategy is the better choice for further industrial applications of our hybrid beads. But not only the cross-section of the composite is of importance, also the interface due to the possible problem of delamination. And here we can see that as the mechanical adhesion theory has predicted, we were able to manufacture microscopic undercuts in which the matrix resin can flow and therefore form sufficient bond strength for our further experimental investigations for the sandblasting structure here. And as we already saw in the previous microscopic images, it's more of a hard edged and irregular surface structure due to the impact of the blasting particles. For the laser surface structure, we can again see the more rounded structure. We can see the results of the melting and the resolidifying of the laser rays on the sheet surface, and here a laser-induced groove. To conclude, also the laser structuring surface strategy was able to generate sufficient bond strength, and now we can see the validation process. Therefore, we started with a preliminary study in which we laminated the sheet metal component with the UD fibers and performed two different experimental configurations of the three-point bending test. In the first configuration, the UD fibers are subjected to compressing load due to the upper position of the experiment, and in the second configuration we performed a tensile load, or we subjected the fibers to a tensile load since they are now in the lower position. And the results show that the maximum tensile load is significantly higher than the maximum compressive load from these three samples. This can be explained with phenomena such as micro-bucklings of the fibers under compressive load. Therefore, in the next experimental investigation, we performed the three-point bending tests on the hybrid bead geometry itself, and therefore we only analyzed the configuration where the UD fibers are subjected to tensile load. It arises somehow as a design guideline for static load cases, that the beads must be aligned in such a way that the UD layer is subjected to the tensile load case. As the results from this figure and from this experimental investigation show, there's an increase in the supportable load in the 3-point bending test, and the amount of the increase is dependent on the thickness of the reinforcement structure. So we fulfilled this necessary condition for the manufacturing of load-dependent sheet metal components. So after the performance of the experiments, we investigated the occurring failure mechanism. As these 4 pictures show, no premature delamination between the composite and the sheet occurred. This holds true for both the lamination processes, here for the manual laminated, as well as for the AFP-based lamination process. It holds also true for all the investigated ply numbers. For example, here 3 plies, again 3 plies, 4 plies, and 12 plies. And it holds also true for both the sandblasting strategies, shown here above, and the laser strategies, here shown for the triple bidirectional strategy and the lower images. Therefore, the mainly appearing failure mechanism was fiber breakage, such as shown here, or here in the border region, here again in the border region, and here again in the border region. And it only appeared after the sheet had already undergone significant plastic deformation. So therefore we can conclude that both the pre-treatment strategies can result in sufficient results for further application of the hybrid beads. So to give a short summary of our research work, our main goal was to show the manufacturability of the hybrid bead. Well, first, the tear-free production of the adapted bead geometry. Second, the surface structuring, which both show a short cycle time with less than 30 seconds for both the laser mechanism as well as for the sandblasting mechanism. And third, there's an application-oriented lamination process with the AFP-based strategy which we used. So we would advise for further implementations of the hybrid beads in industrial applications to use this lamination method. Then the second main goal was to show the load-bearing behavior of our hybrid beads, showing that there's an increase in the maximum supportable force, and then that this increase is dependent on the number of plies laminated on the top surface of the beads, which is a necessary condition for the design of load-dependent component variants. And last but not least, we show that there's no premature failure due to delamination using these structuring strategies, so no additional interlayer such an adhesion promoter is needed for these hybrid beads. To give a short outlook on further research activities, we would like to couple our hybrid beads with the optimization algorithm of Margic, which we had already shown in the introduction of these presentations, and we think that this gives or enables the users to design their components and to integrate the hybrid components and the load-dependent variants in a fast and efficient way into their own components. And furthermore, we'd like to examine an adjustment of our hybrid bead method to various UD-CFRP materials, for example, using glass fibers instead of the carbon fibers. Decrease in the costs can be realized, or basalt fibers propose the ability to use hybrid beads at higher temperatures due to high temperature characteristics of the mechanical basalt fibers. Here we give a short summary of the references used. For example, the optimization algorithm by Magist is described in source number 3. And to conclude, I'd like to thank you for your interest in our research topic, and please feel free to contact me for any further question of the implementation of hybrid beads in sheet metal components.